Industrial facilities are made up of many process systems that work together to make finished products. These process systems can be very complex, with miles of piping and hundreds of system components. Learning how the process systems in a facility are laid out and how they operate can be a big job, but there are some tools available to make it easier. One of the best tools is a diagram. Industrial facilities are made up of many process systems that work together to make finished products. These process systems can be very complex, with miles of piping and hundreds of system components. Learning how the process systems in a facility are laid out and how they operate can be a big job, but there are some tools available to make it easier. One of the best tools is a diagram. One of the best ways to become familiar with a system is to examine a flow diagram of the system. Flow diagrams show the equipment and the flow paths of materials in a system. This information is helpful when you need to perform valve lineups or reroute flow in a system. This is a flow diagram of a crude oil desalter system. This system contains components that work together to remove salt and other impurities from crude oil. We'll use the diagram as we trace the flow path of the oil through the system. The symbols on the diagram can be compared to the actual equipment in the plant. But before we start tracing a system or locating equipment in the plant, it's a good idea to use the diagram to get the big picture of the system. One way to do this is to look at the diagram and find the names of the flows or streams that are inputs to the system and the names of the flows that leave the system as outputs. Inputs or feeds are indicated by arrows that point in the direction of the flows through the system. Outputs or products are indicated by arrows that point away from the system. The major input to this system is crude oil from a pipeline. The diagram also shows that hot liquid from distillation tower F102 enters the system. This is a flow diagram of a crude oil desalter system. It shows the flow paths of material as well as the types of equipment in the system. The liquid provides heat input to the system. The diagram also shows that the system has two other inputs, a chemical called a demulsifier and water. The major output of the system is desalted crude. The diagram shows that it's fed to a refining system. There's also a line on the diagram that is labeled saltwater to waste processing. This line represents the output stream containing the salt and other impurities that are removed from the crude. Now that we've determined what comes into the system and what goes out, we're ready to look at the equipment that makes up the system. By looking at the diagram, we see that this system includes pumps, control valves, heat exchangers, and a vessel called a desalter. Using the diagram as a guide, we can locate the equipment in the plant by following the path that the oil takes through the desalter system. We'll start locating equipment in the plant where the crude oil enters the system, here at pump P101. The major equipment in a system is usually marked with its ID number. So once you're in the general area of the pump, you can check ID numbers on the pumps there to find the right one. Once you locate pump P101, it's a good idea to circle it on the diagram. Circling components on the diagram as you locate them will help you avoid overlooking components in the system. The next component we come to on the diagram is a pneumatic piston-operated control valve. This valve controls the flow of oil to the tube side inlet of the heat exchanger E127. One way to make sure you have the right valve is to first find the right heat exchanger. The heat exchanger is probably easier to find, and it's immediately downstream of the valve. To make sure you have the right heat exchanger, compare the number next to the heat exchanger symbol on the diagram to the number on the heat exchanger. When you get to heat exchanger E127, you can trace the piping from the tube side inlet of the heat exchanger back to the control valve. After the control valve and heat exchanger E127 have been located, their symbols can be circled on the diagram. From heat exchanger E127, the oil goes to another heat exchanger, labeled E102. You can find this second heat exchanger by locating the line from the tube side outlet of heat exchanger E127 and following it to the tube side inlet of heat exchanger E102. The diagram indicates that the heat added to the oil in the heat exchangers comes from hot liquid from distillation tower F102. When the liquid leaves the heat exchangers, it returns to the tower. As we trace the oil flow leaving heat exchanger E102, we see that it flows past a demulsifier addition line and a water addition line. The demulsifier and water are added to the oil to help the desalter do its job. Next, the oil goes through a control valve that's operated by a pneumatic diaphragm actuator. Then the mixture of oil, water, and demulsifier enters desalter V101. As you trace the piping from heat exchanger E102 in the direction of the desalter, you should find the control valve in the piping before you get to the desalter. In the desalter, water, which contains the salt and other impurities, is drained from the bottom of the vessel and goes to a waste processing system. The oil is drawn off the top. Pump P143 pumps the desalted crude from this system on to the next step in the process. Flow diagrams can be helpful when you have to reposition valves because of changes in operating conditions. Making sure valves are in the correct positions is called lining up the valves. To see how you can use a flow diagram to help line up valves, we'll look at an example of rerouting flow in an air dryer system. This is a diagram of the system. The air dryer system takes in moist air from the atmosphere and provides an uninterrupted supply of dry air. These symbols represent the air dryers. Each dryer contains material called a drying agent that traps moisture as the air passes through the dryer. Periodically, the moisture is removed from the drying agent by a process called regeneration. Only one dryer is required to be in service at a time. While one dryer is in service, the drying agent in the other dryer is regenerated to remove moisture trapped by it. Let's see how this is done in this system. This is how the valves are lined up when dryer A is in service. The filled-in valve symbols indicate valves that are closed. So only these valves are open. Moist air enters the system and flows to the bottom of dryer A. Moisture in the air is trapped by the drying agent in the dryer, and dry air flows out of the system. To put dryer B in service so that dryer A can be isolated and its drying agent can be regenerated, these valves are opened. This allows air to pass through the drying agent in dryer B also and out of the system. Closing these valves isolates dryer A. Opening this regenerant inlet valve and this outlet valve allows regenerant to pass through the drying agent in dryer A. The regenerant removes the moisture from the drying agent. Once the drying agent in dryer A has been regenerated, the regenerant valves are closed, and this vent valve and this moist air inlet valve are opened to allow moist air to purge the regenerant from dryer A. Then the valve. Dryer A is now ready to be returned to service. Successfully rerouting flows while a system is operating depends on knowing exactly which valves have to be repositioned and in what order. Using a flow diagram can make the job easier. Now let's see how a flow diagram can be used to help line up valves for a system startup. We'll be using this diagram of a cooling water system as we go through the steps to start up the system. Keep in mind that a flow diagram typically shows the positions of valves during normal operation, after the startup is complete. Other references, such as valve lineup checklists, are typically used along with the diagram to determine actual valve lineups during specific procedures, such as a startup or shutdown. This system provides cooling water for several systems in a plant. Water from a river first passes through an intake screen, which traps leaves and other debris. After the water passes through the intake screen, it comes to a section of piping with two valves. The valves are in the lines that supply the cooling water system we'll be working with. One of these pumps moves the water through a main line. The other pump is a spare or backup pump. The main line supplies cooling water to two process systems, which we have labeled A and B, and a lube oil cooler. We'll concentrate on the part of the system that includes the lube oil cooler. The water from the lube oil cooler is discharged to a cooling pond. Now let's see how the valves are lined up during startup. These valves must be open to allow water to enter the pump suction piping. When this system is started up, only one of the pumps will be placed in service. The second pump will be on standby. However, the suction valves for both pumps are opened so that the second pump can be started quickly if it's needed. In many cases, operating procedures indicate which pump should be placed in service. In our example, this will be the standby pump, so our first step is to make sure the pump's discharge isolation valve is closed. The next step is to fill and pressurize the line that supplies all of the systems that use the cooling water. To do that, the systems supplied by the cooling water system need to be isolated from the main line by closing the valves in their supply lines. This vent valve on the main supply line is open to allow air in the system to escape. In many cases, operating procedures indicate which pump should be placed in service. In our example, this will be the standby pump, so our first step is to make sure the pump's discharge isolation valve. Once all the systems are isolated and the vent valve is open, the next step is to start one of the pumps. According to plant procedures, this is done by partially closing the discharge valve of the pump to be started and then starting the pump motor. Water then flows through the pump suction piping and this check valve in the pump discharge piping. From the check valve, the water flows through the isolation valve and into the main line to fill and pressurize the line. When water begins coming out of the vent valve is closed. Now the next step is to supply water to the lube oil cooler. First, this isolation valve in the oil cooler tube side outlet line is closed, and this tube side drain valve is checked to make sure it's closed. Then the tube side of the cooler can be filled. This isolation valve is opened partially, and this vent valve is opened completely. When water has completely filled the cooler, the vent valve is closed. The inlet isolation valve is opened completely, and the outlet isolation valve is opened. Then this isolation valve is checked to make sure it's open. Water then leaves the lube oil cooler and passes through this pneumatically operated globe valve that regulates the flow of water through the lube oil cooler. Flow has now been established through the lube oil cooler, and the discharge valve at the pump can be opened completely. The valve symbols on flow diagrams often include ID numbers. The valves themselves often have tags that show their identification numbers. These numbers are helpful in performing a valve lineup. ID numbers may also be shown on valve lineup checklists, such as this one. This checklist shows the sequence in which valves are to be positioned in a system. You can use a checklist to identify the valves and then refer to the flow diagram to verify their locations in the system. This is a portion of a procedure checklist for a system that's similar to the cooling water system we just looked at.